Hello everyone. My name is Professor Anil Fernando from the Computer and Information Science in Media Communication and Transmission. So before we start the presentation, so I would like to give you a short introduction to uh, my research on multimedia communication. I'm leading a research team of like 22 people here in Strathclyde on different aspects of media transmission and communication. Main focus on the media communication is based on semantic communication, which will have numerous applications in the future, which I will explain you in few minutes. And apart from that, I'm also working on energy management based on AI, insurance and finance, again based on AI, and next generation networks, especially on quantum communication and Internet of Video Things, and neuromorphic computing and IoT for media applications and digital health applications based on vision and AI. Um, Next, I'm going to give you a short introduction to the semantic communication. Uh, Hopefully, you have some kind of idea about how the basic communication system works. We have the source information, which can be generated some information from microphone or from video camera and some other device. And then the first job is to encode this information. We call this as source encoding, which is used to compress the data to a manageable level before it is transmitted through the channel. So after the source encoding is done, so we have the channel encoding. The purpose of channel encoding is to add some redundant information to protect the source encoded data against the noise which will be introduced in the channel. So after channel coding is done, so we have to modulate the signal. Any kind of digital modulation technique can be used here. And then the modulator symbols are pushed to the channel, and channel will carry this information subjected to the noise. And then at the receiver side, we will do the reverse operation, demodulation, channel decoding, source decoding, and then reproduce the signal. So this is how the information is transmitted in a classical communication system. So what are the three problems of communication? The classical system that we are experiencing today is based on a technical problem defined by the well-known mathematician and the communication theory researcher. We call him as Shannon theorem. So Shannon mentioned there are three problems in communication. One is a technical problem. The idea of the technical problem is to carry the information based on the accuracy of the information sent to the receiver. So we are talking about bit level accuracy of the information. The second layer he proposed is the semantic problem, which is the interpretation of meaning by the receiver as compared with the intended meaning of the sender. So here we are not worried about the bit-to-bit error transmission happening in the channel, but here instead we extract the semantic meaning and recover the semantic meaning as the receiver, which will be uh, consuming less system resources compared to the technical technical problem communication concept. And finally, he also proposed effectiveness problem, where the success with which the meaning conveyed to the receiver leads to the desired action. So in communication, we send some information from A to B for because of purpose. So in the third layer, he mentioned that whether the intended meaning or the action has been taken at the receiver side, which was expected from the transmitter side. So that's the third layer. So far for the last 75 years or so, we have been using only the technical layer, which is defined by the Shannon theorem. So what is the capacity, channel capacity mentioned by the Shannon and his team? C is the channel capacity, which is given by B times log 2 to the base 1 plus signal to noise ratio, O is over N ratio. So where C is the channel capacity in bits per second and B is the bandwidth. and S is the signal power, and N is the noise. So where we don't have control in the channel is the noise, technical noise. What we can control is the bandwidth of the channel and the signal power. So the bandwidth of the channel is getting very limited resource, especially in wireless communication, as you know. But signal power can also be controlled. We can increase signal power theoretically, but practically you can't do that because of the inter-symbol interference or inter-channel interference in especially in wireless communication. So therefore, B and S are kind of a constraint which is limited in the channel capacity on the other hand. So the options, signal power increase, increase in the bandwidth, decrease in the noise, and channel limit. Channel said that there's a limit on EBO and not over signal to noise ratio, which is minus 1.6. You can't uh, go beyond these limits defined by the channel. So at the ratio below this, no modulation or error correction method will allow reliable data transmission. So conventional communication systems with modern channel coding have reached this limit already. So therefore, new solutions are needed, and semantic communication has been proposed to take it over from here, because nowadays we are mainly focusing on machine-to-machine communication and human-to-machine and machine-to-human communication. These kind of wide applications where we do not need the original exact representation at the receiver side. In other words, we can only extract the semantic meaning from the information at the transmitter, and this extracted semantic information can be delivered to the receiver, and receiver can regenerate the information that was intended by the transmitter, and then use it for different applications, for machine to machine or machine to human and human to machine applications. So that's the idea. And you might be wondering why this has not happened before, because of few reasons. Basically, the computing power was not enough to extract the semantic meaning from the transmitter side, and also at the receiver side, the regeneration or generative AI techniques were not that developed in the last few years or last few decades. Now we are in a position to witness the development of AI, which can be eventually used for these communication applications. So this is the communication system for the semantic communication layout, original media. So we have the semantic encoder instead of the source encoder now. So semantics are extracted from the original information. Rest of the things on the lower layer is same as the original layout. Uh, the new thing added here is a semantic encoder, and then we have semantic noise. The semantic noise represents the mismatch between the intended extracted information and the original information. So there is a clear difference between semantically extracted information and the original information, and these are defined by the semantic noise. And at the receiver, the same thing has been applied as before. So the highlighted block here on the upper top side of the figure is the concept that we are extracting for the semantic communication systems. So the objective is modeling and improving performance of the semantic channel such that the volume of data that needs to be transmitted in the tactical channel is drastically reduced. So what are the applications of semantic communications? One is the human to machine interaction, where we can have different applications. I have listed only three applications for your reference: virtual assistants, chatbot, and conversational AI and emotion aware systems. The second most application is it will be on autonomous systems and IoT, self-driving cars will be heavily used in semantic communication in the future because of the limited bandwidth available for massive P2X communications. Smart cities again will generate a lot of traffic in big cities and large amount of people and vehicles are traveling across the roads. So there we can use semantic communications very efficiently. Industrial IoT is another application, double IoT. So machines can communicate their needs daily at any time with less amount of bandwidth. Healthcare is another application, main application where semantic communication will be used, mainly because the information can be regenerated at the receiver for actual information transmission and without uh, sacrificing the security or the privacy of the patients. Wireless and 6G networks, 6G of course will be expecting to use semantic communication significant in their developments in the future. Efficient data transmission, edge AI, and network optimization. All these are the key applications of semantic communications in the future. And the number five is the extended reality and metaverse. So in gaming and AR, XR XR applications and metaverse applications, semantic communication will be heavily used for regenerating of the video and the images of the receiver, mainly for AR, VR collaboration, context-aware virtual worlds, and so on. Number six is knowledge graphs and information retrieval. Semantic search engines and enterprise knowledge management are one of the other main applications predicted for semantic communications. Especially the number seven is the defense and surveillance. And these applications we can use semantic communication very effectively for threat detection and military coordination without sacrificing again the security and the privacy information from the transmission. So number eight is the natural language processing or NLP, summarization and translation, semantic analysis. All these NLP applications has been already developed to some extent in the literature. So there will be a lot of applications in the future in the NLP domain. So digital twins is another application in smart manufacturing, infrastructure monitoring. So these are the typical applications of digital twins in semantic communication. And the number 10 I have selected is the blockchain and Web3 applications. So smart contracts with semantic logic, decentralized knowledge sharing, and these are some of the applications of semantic communications which can be used in the future or already is being happening in the last few years. So where the future is heading is there will be a lot of semantic communication applications where I have not listed here. So main applications will be brain computer interfaces or BCIS, direct semantic through transmission, and general AI collaboration, machine exchange, abstract information for problem solving, and machine to human and human to machine communications. And this is a classic example on how the vehicle to everything or V2S communication happens. A lot of information is being transmitted by every device, every car, and every people, and which will generate a massive data transmission in mobile networks, and which will be having a big problems of managing the traffic with the required QA. So therefore, semantic communication will be expected to solve these problems because we can scale down the communication as it needs, sending only the semantic information for decision making and so on. And this is again another application of autonomous driving. The same concept can be used here. And this healthcare monitoring for dementia patients, you can see that patient has been fallen in the bathroom, but without revealing the personal data in a private place like a bathroom, we can regenerate same information at the receiver side without generating the information which is sensitive to the fallen patient. So this is a classic example of how semantic knowledge can be used in healthcare applications. So I have listed a few applications, few main applications for semantic communication in media. So here I am going to explain a framework that we have developed for image transmission. You can see on the left side, there's a transmitter side. This is the original information. We extract the semantic information using semantic segmentation, and then we generate a kind of a map. We define this as semantic segmentation map, and we channel encode it, like I explained in the beginning, for providing the protection through the channel. So channel noise is added during the transmission. Channel decoder regenerate that semantic map, and then This can be corrupted slightly depending on the noise that in the channel. And then we have a GAN network here, generator and discriminator. This information is applied to generator, and generator and discriminator jointly regenerate the information which was intended to send by the transmitter, and this is a generated image. And then we have the shared knowledge between the transmitter and the receiver. Some kind of predefined information is shared between the transmitter and the receiver to regenerate the information, which is the common concept in semantic communication. So you can see that generated image and the transmitted image has a very high correlation in the semantic domain. If you consider pixel-to-pixel representation, there can be differences, but if you consider semantically regenerated information, which has the same information as the intended information sent by the transmitter. In this case, example, a lady is with a horse in a green grass field on a sunny day. The same information is generated at the receiver side. So these are some of the information that we have used for the generation purpose based on the GAN. And some more results here, you can see that the information can be significantly reduced from 100 kilobytes to like 5 kilobytes because we only need to send a very small amount of data for sending the semantic map to the receiver. So basically, the bandwidth can be reduced uh, about 20 times. And these are some of the original information on the left side, and the semantic maps generated for the ground truth data, and then the degenerated information at the receiver, which will have similar information which was intended by the transmitter. So this is another example that we have done to prove that machine can understand the information effectively when it comes to semantic communication. In this case, we have used means dataset, the number dataset, to train a semantic network. So we have semantic encoder. In this case, we have used an autoencoder and extract the latent representation of the image, and then channel encoder, modulated, send it to the channel, and demodulated, channel decoded, and semantic decoder, and regenerate the information. If you consider these two images, so semantically they are very much same like the original information. And then we have used a CNN-based image classifier to classify the information in the image. So we have mimicked the machine perception using a CNN classifier here. And then we have run this experiment under different noise conditions. You can see that the performance has been much greater than the conventional image transmission system like JPEG. So there's a considerable performance gap between the semantic communication system proposed and the JPEG for different noise levels. Same thing is considered here. We have considered the bit rate and the PSNR graphs. You can see that the semantic decoder can tolerate all this noise very well and regenerate the image quality to a very high value. Same information presented in a different way against the classification accuracy and the signal-to-noise ratio. So this one is another application that we have developed. Is called the region-based scalable image compression using semantic communication. What we have done is we have extracted the main semantic information from the image. In this case, two buses and birds and the aeroplane. And then what we have done is we have extracted this information and provided a higher bit allocation for this semantically important information, and the background is compressed using a high quantizer so that the background quality is a compromise against the actual semantic objects. So you can see that by doing so, the semantic meaning extraction has been preserved, where we reduce the bandwidth, unnecessary bandwidth for understanding this information or presenting this information as the receiver has been very well managed. So this is a very big topic, but I have tried my best to provide you some kind of insight information to understand the importance of semantic communication. And here I'm going to very briefly discuss about the current and the future research on semantic communication. So one of the problem is the optimization of the deep neural network for image extraction, semantic extraction, and joint source and channel coding, which are completely new topics in semantic communication. Several AI-based machine deep learning techniques can be used in semantic extraction and information regeneration, CNN or convolutional neural networks, GAN or generative adversarial networks, autoencoders, vision transformers, or semtext that we have developed, and diffusion models. So better compression rates in image compression compared with conventional lossy image compression methods are the key to the success of the semantic image communication. Distributed coding of images with semantic encoders with better bit budgets is another uh, main domain that will be developed in the future. So when it comes to video, it's more difficult. Optimization of deep learning methods for video coding and transmission. Pure semantic-based encoders for video coding and transmission. Semantic communication deep learning-based reusable coding systems. So these are the high demanding areas when it comes to video compression. Scalable semantic video transmission systems, distributed semantic-based video transmission systems, test-bed for video semantic systems for machine-to-machine, human-to-machine, and machine-to-human applications. Complexity-aware semantic video encoders are the next main development in the semantic video communication. So these are the possible application in XR, like I told you before. Testbed for XR-based semantic communication systems will provide a lot of opportunities for media creation and media transmission in the future. So one of the main problem is the semantic quality metrics. We don't have any quality metrics available at the moment, a reliable quality metric available at the moment for semantic understanding of the received image. So that's another hot topic in the future. And semantic noise modeling, which is another main domain. If anybody wants to work in semantic communication, semantic noise modeling is another big topic that needs to be addressed and modeled mathematically and verified using a proposed kind of a channel model for semantic noise modeling in communications. So I think I have tried to explain the importance of semantic communication in media compression and transmission. So hopefully you have understood these concepts very well. And then if you have any problem, just communicate to me. My uh, address and the email address is given here. So we are open for collaborations in semantic communications or any other domains related to machine learning, AI, and the vision processing and communication. Thank you very much. Have a good day. I'm signing off, Professor Anil Fernando from the Computer Science Department in University of Strathclyde. Thank you.